don't grab your homework, it starts piling up in the folder, and then the folder starts getting really big, and that's kind of hard to manage. So please make sure that you grab your homework from the folder.
And at the end of the semester, Soraya and I, we will go to the campground and burn it. Okay. So you're supposed to have read the When Will I Ever Use This essay. So go ahead and take a minute and talk to your neighbor about the ideas you had about that essay. So what are the things you liked, things that were powerful for you, or things that could be added, or whatever. So go ahead and talk to your neighbor.
I mean,
Yeah, sure. What's your name?
Chase. Anna. The one that usually do things.
I think it helps me like not only in this class but the other classes. I feel like I don't really think it's like I can maybe I should actually do a little bit more.
Yeah. I really like the idea that like you don't know what you don't know. And so yeah, just doing our best in each class because I didn't take trig very seriously in high school. It's come back to bite me.
Yeah.
And like just today's dynamics, I was doing like we had these projections and stuff, and I was like, you know, because I didn't pay very much attention because I thought it was the only time I was getting used to it. Yeah, it definitely made sense. I thought it was good.
I like the examples we had in there, like food and stuff. Like
Yeah, so Steve Jobs.
Yeah.
Very nice. Yeah, it was really interesting.
We do see lab at 6 times.
Not actually.
Really? But it's the time I can do it. That's sweet. I can learn. Or easy, I'm doing it right now. Yeah. Yeah.
Okay. You're welcome to volunteer your neighbor for this, but any comments you want to share with the rest of the class? The things that you heard or things that you thought? Yes.
I like in the summary kind of portion when it gives some insights from Joseph Smith, and he talked about how knowledge is revelation and that knowledge is power. Really like, and I don't remember the exact wording, but he talks about how like God has power over all things because he has knowledge of all things.
That's right. The power comes from the knowledge.
It's all about the knowledge, really.
Yeah.
I thought that was awesome.
I thought so too. Thanks. Okay. Other comments? Yes.
I really like the discussion on that you don't know what you don't know. I actually did something very similar for senior project way back when in high school, and so that was a different perspective that a lot of people didn't really give me when I went around and surveyed them.
Yeah.
The one that I saw most often was just more that math helps you learn tools that like help you think and problem solve. You don't use specific things, but it's interesting to see that sometimes you do.
Yeah. I've heard that argument that, oh, math just makes you a good thinker. And I think it can, but if that's all we're getting out of math class, I think there's a lot more fun and interesting ways that we could learn how to think than just doing math, but that's all we get out of it. There's lots of fun brain teasers and other problem solving kind of things, activities we could do rather than subject people to algebra. I mean, like, if that's all they're getting out of it, right? Yeah, so I don't like that argument that, hey, you're learning math just to learn how to think. It's actually a lot more than that. Like, you're learning math to learn math, and math can be very powerful. Now, we don't usually teach it in a way that helps you use it. That's a different story. So that's what I'm trying to change. School math, real world math is very different than school math. So school math isn't very good, but math is. Okay, there's another hand up somewhere up here at the front. Okay, other comments? Or, yeah, do you want to do it?
I was just gonna go along the same lines. I just like the story of Steve Jobs a lot and how he's able to connect the dots looking backwards on like behavior and all that. Just very insightful, and it had a lot to do with the you don't know what you don't know.
Yeah, powerful story. Who would have thought that him just wanting to take a like free class would have had such a big impact on the world of computers? Pretty crazy. Okay. Any other last comments? So the essay is really about a theory of learning. It's really about a perspective of learning that we should really hesitate to say, oh, I don't have to know this. There's not really a good reason. You should err on the side of learning, especially from a gospel perspective. It's part of our progression. So we are trying to learn and learn a lot. Of course, we need to make choices about what's most important to learn. The choice of not to learn should be a choice. What you're prioritizing. Okay. So this chapter 3, is moving into the algebra of matrix algebra. We've already used some algebra, but we haven't. We're going to be moving in. We're going to formalize it a little bit more. We're going to have an algebra of matrices. We've really been using the algebra of. We have some algebra vectors that we've been using, some algebra like systems of equations that you're already comfortable with. But we're going to be doing a different kind of algebra, matrix algebra. So just a little comment about algebra. There's tremendous power with algebra. We use it to represent properties and rules of numbers, for example. We represent unknowns, and then we set up and solve equations. So that's pretty powerful. We can represent relationships of quantities and show how different things are, the value of your money is related to your principal and the investment rate and how long you invest. And we can also use it as a thinking and reasoning tool. In chapter 3, we begin to build up these same tools for matrices. You've already learned for real numbers. We can use it to represent properties and rules of numbers. I should have parentheses around there. So this is a transpose operator we'll talk about in a section or two. We can represent unknowns and set up and solve equations. So we can do, if we want to solve for x, we can try something like that. We can represent formulas to show how quantities are related. This turns out to be one of the most used and powerful matrix equations. And we can also use it as thinking and reasoning tools. The same way that when you get comfortable with all those other things, it just becomes a part of the way you make sense of things. But along with the power comes the difficulty. Algebra is a real nut. It's a really hard nut to crack in terms of teaching it. It helps students understand really well. And part of it is because of this issue. We have symbols here, but you are required to bring the understanding to the symbols to make sense of it. And when you don't do that, you start to overgeneralize. So, for example, if this was a times b squared, you could write it as a squared times b squared. But students often start to do this. In fact, I usually see this a few times every exam on my calculus class. Even here at BYU. Okay. This is the matrix A multiplied by the matrix B. A times B is not necessarily the same as B times A with matrices. But you've already been trained to think about that in terms of x and y. Oh, it doesn't matter if I write x times y or y times x. Okay, you have to be careful how we're going to generally think. Distributing here, that's also going to be an issue. This isn't necessarily the same as this. So not all rules that you learn with the algebra of real numbers is going to apply. So we have to be careful. The most used operation in linear algebra is matrix multiplication. It's the hardest to get our head around. It's the one we use the most powerful one. And that's what we're going to study the most. But I do have couple quick slides on addition. So here we've got a 2x2 matrix, 2x2 matrix. We add it together. You would have read about this. How do you add matrices? Component wise. So the the first row, first column entry here, you add to the first row, first column entry here. So 1 + 3 is 4, 2 + 1 is 3, etc. Why does that make sense? Well, if you put some units on here, then it can make sense. If this is the number of servings Alice has for breakfast in terms of peanut butter and bread. So one serving of peanut butter, 2 servings of bread. Bob has 2 servings of peanut butter and 2 servings of bread for breakfast. Well, then they eat peanut butter and bread for lunch. Okay. Bob has a really dry sandwich. 5 pieces of bread and 1. Maybe it was those. I don't know. Okay. So anyway, these are the servings for lunch. Well, if you add them together, you're going to get, component-wise, you're going to get the total number of servings for Alice and Bob for peanut butter and bread. It makes sense for, oh, Alice had 1 serving for breakfast, 3 servings for peanut butter for lunch, so she has a total of 4. Alice has a total of 4 peanut butter servings. So adding components makes a lot of sense when you're adding. And you can see why the matrices have to be the same size when you add. It wouldn't make sense to have, oh, this is Alice and Bob, and then this is Alice and Bob and Chuck. And you're like, well, what do you do? Like, what happened to Chuck at breakfast? You could add 1. You could say Chuck wasn't there. He had 0, 0. He was fasting because he had a no, what's that called? The cholesterol test that morning for with the doctor. So 0, 0. But it doesn't make sense to add matrices if they're not the same size. Okay, let's dive into matrix multiplication. How many of you before this class, how many of you have seen matrix multiplication? Okay, and how many of you, when you learn matrix multiplication, thought, why in the world do you multiply matrices the way that you do? I know I did. I'm like, why in the world? This makes like no sense. Like, why did they make this up? Okay. Well, it's actually not too hard once we understand this piece over here. So these are things we've already worked with. So we have an augmented matrix, which can represent a system of equations. And we can represent this system of equations by factoring out the x, y's, and z's, and then putting the coefficients into vectors as this. X times this, plus y times this, plus z times this equals that. Okay? So we have 3 different ways that we can think about this. We have a new way now. We can think about it as the matrix, which is the coefficient matrix here in the augmented piece. So we think about it as this matrix times a vector of unknowns equals this. And it's the operation of multiplying is most closely aligned. So this means, well, I have x of this column, and I have y of this column, and I have z of this column. So if these are actually numbers, you can actually start to do the computation. If this was 1, 2, 3, you can be like, okay, I have 1, 1 plus 2, 2 times 3, 3, and then add those together.
So you go column, rows.
The question is, you go columns or rows and then columns. What do you mean?
Because you can't switch them, so you have to do one first. Is that it? One of those ways you can't.
But what do you mean you can't switch them?
Like,
I'm just trying to make sure I understand.
like in matrix multiplication, right? You said that A times B is now A would be A. So how-
Oh, so there is a way you can think about going forward. So I can think about this times this and this times this and this. Extract them up that way. So if you want, but trying to put the x, y, z over here, we'd have to write it x, y, z sideways for that to make sense, because then you'd have an x, y, z times this, x, y, z times this.
So
you can, but you have to
multiply the
transpose
column
them.
of the first one, row of the second one.
Yeah, so you have rows here, columns here.
Yeah.
So row, column. They're actually a dot product. You would have read about that in the section. Like each of these entries is actually a dot product. So this row vector here and this column vector here, we get dotted. So it's a dot product of these 2 vectors.
In that case, is for two matrices A and B is A times B equal to B times transpose A, or A transpose?
There's something close to it. Okay. So it's not yet. Nice. Okay. I have some specific, I have some that don't have X, Y, Z, so we'll get into the computation. But this helps to, if you have this in mind, and we have a matrix times a vector, you can go back to help it so it makes sense. Okay, so this represents X of this column, Y of this column, Z of that. Oh, actually, I think they have a better. No idea. So your first column here gets multiplied by your first entry here. Your second column by your second entry. So it's a linear combination of the columns. That's what you're doing when you're multiplying. We're just taking a linear combination, and this tells us how much of each of the columns is there. There's also something a little more subtle happening here. We can think about this in terms of rows in a system, like rows of equations. The rows are equations, or we can think about linear combinations of columns. But now we can think about it simply as a multiplication. It's a complex multiplication, but we just have to think about it. Oh, this is a matrix, one multiplication times X, Y, and Z. We don't have to choose to focus on the columns or choose to just focus on the rows. We have a new way of thinking about this. So here's a familiar example if you've read the peanut butter book. So we're going to multiply. So this 1 represents one copy of the 15(8) vector. 2 copies of the 1.53. Mistake. That should be 3 right there. So I missed that in the first class. And then when you add these together, 1 times 15, 1 times 8, 2 times 0.5, 2 times 6, then you add those vectors together, you just get this. And you get 18, 14. So, and this makes sense if you pull out units again. So this is fats per fat, the amount of fat per serving, the amount of protein per serving. This is for peanut butter, this is for bread. Yes.
So it should be 2 times 3. And 2 times 6 is also not 14.
You add.
Right, it's supposed to be 1 times 8 plus the 2 times 3, which would be 6. And
Right, okay.
yeah, so that should be a 3. And this should be a 3. So, and this is the servings of peanut butter, and this is the servings of bread. The units tell me, oh, if this is the servings of peanut butter, I'm only working with the peanut butter column here. It only makes sense to multiply a 1 times 15 and a 1 times 8. And it makes sense to multiply. I have servings of peanut butter times fat with the number of servings I multiply for the units to work out to get fat. Sounds good. I'm trying to get that. Don't get that if you do that. Different meaning of
The
that.
macronutrient.
Yes, there you go. Thank you. All right. So this is 1 serving of peanut butter, and this is the fat in peanut 1 serving, and this is the protein, or protein in 1 serving. 2 servings of bread. This is the fat in 1 serving. It's supposed to be the protein in 1 serving, and then you go find on this one. So usually students will just start to jump from here to here. So they have something like, oh, I'm going to take this, multiply here, add them together. So 15 times 1, 1.5 times 2, add them together. Oh my God, 18. 8 times 1 is 8. 3 times 2 is 6. 8 plus 6 is 14. So you start doing that. Okay. Any questions about this? You do end up like this is all your fats here and all your proteins here. So it makes sense that this is your protein and this is your total fat. Okay, so with your neighbor, talk about which of these makes sense and why or why not. And in the last one, if it makes sense, what should you end up with? Actually, do the calculation if it makes sense. Go ahead.
Two makes sense to me. 2 makes sense.
Yeah, they just
It's
don't.
been the same. I know the chat.
If I have to do it.
Second.
Yeah, instead of just doing like this, column goes to top left.
Oh.
Actually,
Or you can do.
Do it.
18, 14.
Oh, if you try to do.
Second one actually doesn't.
Yeah, why not?
You just add to
It's
it.
110. You do rows of the first
Second
one.
one.
The second one.
Like I know handles, but
Just one column.
or no, it would,
Yeah, it would.
because there's three. Yeah, okay, that one makes sense. Like, that makes sense.
Third one you can't. Fourth one would.
Like doing the actual matrix, combine the rows.
It makes so much more sense to do two metrically like that.
Yeah,
But with that.
but you would need to.
If you just add a 15 and a 1.
No, oops, no.
Yeah.
I have two columns.
So there would be. These like three,
Okay,
but it would be.
all right, first one. Well, we just did that one, so that one makes sense. So, what about this one? We've added a row. That first, for the first matrix, we've added a row. Does that make it so we can still do this?
Yeah.
Yes.
Heard the no, heard some messes. Let's think about this in terms of context. If this was peanut butter and bread, and this was protein and fat, what do we add carbs? Can I have protein, fat, and carbs to keep track of that? Yeah, and then this, when we multiply, still match up my servings of peanut butter and my two servings of bread, and I have three things to add together to, well, three rows to add together, and I have a total of protein, fat, and carbs. So this does work. So yeah, the 1 times 15 plus 2 times 1.5 gets us our 18. 1 8 plus 2 3s gets me 14. 1 1 plus 16 gets me 17. So that works. So could I add on another row here? Could we do calories?
Yeah.
Could we do vitamin C?
Yeah.
Yeah, we can just keep adding as many as we want. But can I add a column? No, because then I have trouble. I've only got 2 values here and I'd have 3 columns and I just wouldn't know what multiplication to do. All right, how about this one? No, even though I've got 3, 3, 3, this tells me, if I think about serving, this tells me how many servings of maybe peanut butter I have, how many servings of bread I have, and then how many servings of what? Yeah, I can do 1 times 15, 2 times 1.5, but then I don't know what to do with that 3. Like I just have nothing to line it up with. So, or maybe is it 2 times this 15 and 3 times 1.5? Then what do we do with the 1? Like, I'm just stuck. So this is undefined. This one does not make sense. Okay. All right, how about this one? Make sense? Yeah, here we've added a 2, 2. Without this, you'd think we should just end up with 18, 14, 17, because this looks exactly like this does. Right? So what happens with this 2, 2?
Add 15, 8, 1 to 18, 14, 17.
So 15, hold on.
Add 15, 8, 1 to 18, 14, 17, and you stick it on the edge with the 18, 14, 17.
Okay, so okay, let's do the calculation from the beginning. So I've got this column. So I have an 18, 14, 17 for my first column. But then I can do 2 times 15. Let me write this down. So. Okay, now what was it? One. Five. 8. Okay, so let's do this. So I match up. Well, what size is this going to be? What size of matrix am I going to have?
Right.
So how do I know it's a 3 by 2? So every row here, I can think about every row here being multiplied by a column here. And I'm going to get an entry. So this, I'm going to have this row, I'm going to get a number. This row, when I multiply, I'm going to get a number. This row, I'm going to, well, I get a number. Well, at least I'm going to get at least one number. So I have to have at least 3 rows to put these, when I multiply these 3. Then how many columns am I going to have? Well, I'm going to get 1 column when I multiply them by this column. I'm going to get another column when I multiply by that one. So in the book, it did this thing. This is a 3 by 2. This is a 2 by 2. So these things have to be the same to make it so you can actually do it. So it's viable. This tells you the size, but you can just start multiplying it out, and you're only going to have so many things, so many multiplications, and put them in a reasonable spot. So I have the first row here and the first column here. That goes in the first row, first column in my new matrix. So that's going to be 15 times 1 plus 2 times 1.5 is 18. 8 times 1 plus 3 times 2 is 14. 1 times 1 plus 8 times 2 is 17. That was my first row. That guy was my first, that was my first column times all of my rows. And now 2, 2, I can think this 2 times this 15 will give me 30. This 2 times my 1.5 will get me 3. So I have 33. Then 2 times 8 is 16. 2 times 3 is 6. So 16 plus 6 is 22. And then 2 times 1 and 2 times 8. So that'll get me 16 plus 2 is okay. So they're multiplied now. Questions? Yeah, this is not the hardest section we'll be covering. So here's an example. Here's how you could put this in a context. We didn't just have servings for one person, we have another person. So this matrix here, instead of just servings, it's servings for Alice, servings for Alice, and servings for Bob. So this still has the peanut butter, bread, and fat, protein, carbs information. And when I multiply, I'll have the total amount of protein, fat, and carbs Alice ate, and the total amount of protein, fat, and carbs that Bob ate. So, and what if I had Chuck on here? Is that okay? Yeah, we could have Chuck. That's okay. We just add a column here, but it would just give me one more column to multiply with. And it's just fine. I can't add servings down this way. Because this is servings for peanut butter, servings for bread. Wouldn't make sense to have a number of servings for something else. Okay. I know it really would be nice. This would make so much more sense if we had XYZ written out this way. And then you could just go, oh, X times that, Y times that, Z times that. It would make a lot of sense. It turns out the algebra is not nearly as nice if you try to do it this way. One reason is, here we started with this row vector, and we multiply by this matrix, And then we don't end up with a row vector, we end up with a column vector. So if we define it this way, then we have to take that row vector at the end, and I'm sorry, the column vector at the end and turn it back, switch it back. So that's a problem with that one, is we should get the same kind of vector that we started with multiplying, but here you don't. You started with the row vector and you end up with the column vector. And so, like, does that really make sense? So then you definitely translate it back. So you can try it. You can do this. You can think in your mind, okay, twist, and then do it, and then twist it back. And figure out how to take into account if it's not just a vector. But anyway, lots of things don't work out very well this way, especially when you start multiplying a matrix times a matrix times a matrix. When you pick two, you better have it work out so that you don't have to do some transposing or anything in the middle when you do that multiplication. Okay, does someone have a question? Yes.
When you multiply three matrices by that, is there a certain order you have to do them in order to get them to all work so that like the column and rows line up?
Great question. We'll learn that it actually doesn't matter. So as long as it like A times B is doable and B times C is doable, then yeah.
Then it's A times B.
Then you can do A times B, and then you can, or you can do B times C first and then multiply that by A. So it turns out we're okay either way. That's kind of the next section, is to develop the properties of things like this. So I basically just told you that matrix multiplication is associative. So it doesn't matter if we do A times B or B times C, at least if the sizes matter. At least if each of those two things are the pairwise multiplications, as long as the sizes are such that they're different.
Right.
Okay.
So it'd have to be like the first one is size IJ, the second one is size JK, and the last one is size KL.
Nice. Yep. Okay. Other questions? Any other questions about anything from this chapter, this section? Before we dive to our last little thing. I use have questions.
It's cool.
Okay, there's a matrix. Tell me what the transpose of that matrix is. Tell your neighbor.
Top row, the first one.
Sensical.
I mean, I guess you
adding
don't.
information to A anyway.
Oh, shut up. Do you like?
Like you don't have information.
All right. If this is a 2x3 matrix, what's the transpose going to be?
A 3x2 matrix.
It's going to be a 3x2. And what's my first entry going to be? When my 1-1 entry, so we call that like A11 or A1 comma 1. Little a looks like a 9. It's 1. What about this entry right here? 4. If I transpose this, my rows, my columns here become my rows over here. So 1, 4 becomes 1, 4 there, 2, 5, 3, 6. A lot of students think about reflecting it over the line. Oh, reflecting it over this kind of y equals that diagonal line going down to the lower left, so y equals the negative x kind of line, and you reflect that. So your diagonal lines from the diagonal entries there stays. All right. How about what entries? What entries would these values need to be? That I have boxes there if this matrix is symmetric, or to make this a symmetric matrix.
3, 4.
So you tell your neighbor.
2.
It's like the floor. Picture of
What do you need to add?
Where when you get like
CD goes.
Yeah.
Okay. So using this notation here of little b 2 comma 1, that's the entry in the second row. We always do rows first and then columns. So second row, first column. What would that be? What would that need to equal? 2. 2, because this is 2. The definition of a symmetric matrix is that the transpose equals itself. What do we need so that B transpose equals B? Well, when you transpose this, then this number will come here, that number will come there, this number will come there. The blanks will go up there, right? They'll switch. So that tells you how to fill those in. 3 comma 1 would be 3. 3 comma 2 would be 4. And in general, for a symmetric matrix, B I comma J equals B J comma I. So this B3 2, that better be the same as B2 3. And is it? 2, second row, third column, 4. Yeah. So B3 2 down 3 over 2 the same as down 2 over 3. So if you switch the indices and they're the same for all those, that's another way of seeing that it's a symmetric. Okay. Yes, Ben.
Why is the transpose of a matrix significant?
So that question was, why is the transpose of the matrix significant? So we'll use it for a few different things. One way that we're going to come up really soon is when we have dot products, it gives us a nice way to write them as a matrix product. So if I have, like if U equals 1, 2, 3, B equals -1, 0, 5, I can think about U dot V, right, this dot product, or I can write it 1, 2, 3 dot -1, 0, 5. Okay, that makes sense. But if I have an equation like A times U dot V, you actually have to think whether that even makes sense. Like if the sizes are such that these make sense, then how do I write? No, that's the best. Yeah, I don't know if that's the best. But I can rewrite that U dot V so that it is. So I can rewrite that as U transpose dot V, and now that's not a dot. That's just matrix multiplication. Now I just have 1, 2, 3 -1, 0, 5. Okay, so that's one of the first things we're going to use it for, is we're going to have dot products intermixed with matrix products, and sometimes it's nice to turn them all into matrix products to do the algebra. Another situation is when we have, it's really nice if you can create matrices whose inverses are their transpose. Those are really, really special. It makes solving equations really, really nice. So that'll come up later. Those are two situations.
Question?
Yes.
What would you get if you had U times V transpose? Is that something that's significant, or is that just a gibberish matrix?
No, because U dot V will just be a constant. And then you just have a number, and the transpose of the number is just a real. The transpose of a real number is just a real number.
So I'm referring here, like with the notation you have, right? The U transpose times V gives you the dot product. If you were to do U times V transpose, that gives you a matrix instead.
Oh,
like,
sorry.
is that matrix significant?
I thought you were talking U dot V parentheses transpose. That's what I was thinking in my mind. So, yes, we'll get to those. That's called an outer product.
Okay.
So sometimes the dot product is called an inner product. It reduces down to a single value. that is called an outer product, and we'll use those to. There's ways to make certain matrices with the sums of outer products, and they have some special properties too. So we'll get to there. That's much later in the course. Yes.
What's the inverse of a matrix?
Sorry.
You mentioned an inverse of a matrix. What is that?
That's 3. That's where we get to 3. When we get to 3.3, we'll talk about inverses. But quickly, we've written AX equals B, where X and B are vectors and A is a matrix. And I said, well, earlier I said, well, that's a lot like 3x equals 5. Right? How would you solve that equation? 3x equals 5.
Divide by 3.
Yeah, what does it mean to divide by a matrix? Like that's why you wanted to kind of get. Can I take A over A X bar equals B? That's really hard. But we might be able to multiply both sides by a matrix to kind of cancel out that A, and that's where the idea of an inverse.
Makes sense.
Yeah.
A matrix that you multiply the matrix by, that would give you 1.
Yes, although it's usually the we'll call it the identity matrix.
The ones along the diagonal.
Yes, ones along the diagonal.
Okay.
Yeah, so we can get that. So, right, but yeah, these are ideas we're building up to in this chapter. Okay. Great. Other questions? Don't read my email. Oh, close your eyes. Hold on. Close your eyes, everybody. Dang, ruined it. Hey, all right, here we are. We've got Bart Simpson. Got a picture of him, and we're going to transform him. Okay, we're going to do this with a matrix. So I have 1, 0, 0, 1. This is what we call the identity matrix. Did it talk about the identity matrix in this section? Yeah. Okay. Yeah. So we have the identity matrix. And then we can multiply it by coordinates on the grid, and we'll get a new coordinate. Okay. So, what I'm going to do is I'm going to change this value here, the upper left, the 1, 1 entry, to 3, and this lower right one, the 2, 2 entry, to 2. And you tell me what's going to happen to Bart. At least what's going to happen to B here and C here. The big B, the capital B and capital C. What's going to happen to those points? This is the point. I can represent this as a vector 2, 0. I can represent this as a vector 0, 3. So what's going to happen to these if I have? Did I say this was 3? 3, 0, 0, 2. Okay. So think about that. And then when you have an idea, talk to your neighbors. Share your idea with your neighbors.
So did I, bro.
It helps you guys out a little bit. Look at the equation now. He has the equation for A, which is the 0, 1. Thing is, that's that matrix, a transformation matrix, that identity matrix times 0, 0.
Okay.
Look at the point.
All right, someone got an idea? Let's start with this point 2, 0. 2, 0. What's going to happen to that point if I multiply it by the matrix 3, 2, 3, 0, 0, 2? Yes. Oh, sorry, I thought you were raising me. You have an idea? Can we just do the 3, 0, 0, 2 equal 3 multiplied by 2, 0. What am I going to end up with?
6.
6, 0.
2 times 3 plus 0 times 0. And then I'll have 2 times 0 plus 2 times 0 equals 6, 0. What's like 6, 6 or 0, 0? 0. Gosh. 6, 0. So should end up at 6, 0. So I'm moving. Before I move those, let's do. Let's look at the other one. 3, 0, 0, 2 by 0, 3. What's going to happen here? I get 0 times 3 plus 0 times 0, and then 0 times that 0 plus 2 times 3. What do I end up with? 0, 6. Okay. So this 2, 0 should end up at 6, 0 out here, and the 0, 3 should end up at 0, 6 right there. Okay, let's see how close we are. Is this one the 3 or the 2? No, I can't remember.
No, it's supposed to be 3.
There we go. One way to think about this is we didn't just move B and C, capital B and capital C. What we did is we moved every point in the whole plane. We stretched the whole plane out that way. We tripled the length that way, and we doubled the length this way. So that's why like all the points in the picture moved. So okay. Now, what do you think is going to happen if I move this little b here? So that's this entry here. So it's 3, and then the little b number that I'm going to change, 0, 2. It's hard to visualize. This is called a shear transformation. Okay. And then what if I move C? Here, let me move B back to the
shear transformation.
If I move C, it shears it in the other way. And then I can move both of them and I can get some cool stuff. Okay. So I'm going to put Bart back to the back to his original position, and I want you to figure out a matrix that I could multiply Bart by and get him facing this direction. Okay, you can work with your neighbor.
Reducible came out with a really good video about the 3 cosine transforms.
Yeah. You just want JPEG.
Oh, really? Zeros. Stretch out.
Yeah, you can stretch him too if you want, but yeah, reflecting along the y-axis would be sufficient.
You want them in the same spot reflected, or?
So that's, I don't care, whatever you give them. So that question was, do you want him in the same spot? So I can think of like moving him over this way and then reflecting him back like that, and then you get the same spot. But you don't need to have him in the same spot. And it turns out that no matter what values you put in there for A, B, C, and D, could you get that? It's more than a matrix multiplication. It requires some addition, some matrix addition, or matrix subtraction to get him to move someplace. Right now, this point 0, 0, the origin. No matter what I put in here, it will always end up with 0, 0. So if I'm doing multiplication, then that point will always stay in the origin. Yes.
This is kind of the idea of how 3D animation works, because it's like multiplying the vectors by a bunch of other vectors.
Yes. In fact, if you take the mathematics of 3D animation class, like 452, all it is that this linear algebra.
Would a character just be a like, see that?
Yep, and a character in 3D animation is just a huge matrix of vectors. And they got a bunch of 3 values, and then for each point, and then they have a whole list of those points, and then it triangulates it, and it creates the web. We'll share some of that stuff later. So anyone have an idea for me what I should change? What one to negative one? A. So if I change A to a -1, or actually any negative value, it gets pointing in that other direction. And you could reason through that. Oh, time's up. But yeah, you can start doing some multiplications to figure out what's happening. Have a great day.
Then it's like 20 minutes later.